In this example, we're supposed to use identities to simplify the expression the sum of 2x squared plus y cubed squared. So the first thing I'll have to do is identify which identity this is going to follow. Since we have a perfect square there, we're going to be using, or not perfect square, we got a binomial squared, we're going to be using the one that has the binomial squared. So this one in the middle of my list of identities, and we'll be starting with this side, the side that we're given. So just rewriting that out, we have the formula written out, and now we just have to identify A and B, and then follow through applying this identity. So A, based on this pattern, it will be the first term in the parentheses that's being squared, and B will be the second. So our A for the formula will be 2x squared, while B will be y to the third. So now we can actually apply this formula. So if we do so, we have a squared, so we're going to have 2x squared squared. And you'll notice that originally the formula has plus minus. We still have the plus minus. What that tells us for this particular identity, or how that's used, is it tells us whether we keep the sign the same or change it or just keep a specific sign. Since the plus minus is the same on both sides of the equal sign, we'll keep whatever sign we originally had. So we're going to have plus twice AB, so 2 times A, which is 2x squared, times B, which is y to the third. And then lastly, plus B squared. So plus B squared, and B is y cubed, so y cubed squared. Now we just have to simplify this a little, applying exponent properties. So we have the power of a product, distributing the exponent on the outside to both bases on the inside. 2 squared is 4. And when we raise x squared to the second power, we multiply the exponents, giving us x to the fourth. The middle term, we just have to do some multiplication. 2 times 2 is 4, and x squared times y cubed, we can't really do anything with that. In the last term, we have a power of power again, so we'll multiply the exponents, giving us y to the 6. And that is it. In this example, we're going to prove the algebraic identity. The sum of perfect cubes here is equal to a plus b times the quantity a squared minus ab plus b squared. So as I do this, whenever you want to do a proof, a lot of the times you want to start with the more complicated or the larger side and then work towards the smaller side. So we're going to start with this side, and we're going to simplify algebraically and hopefully end up with that side. So starting with a plus b times a squared minus ab plus b squared. We'll distribute things out. So a times a squared is a cubed. A times negative ab is negative a squared b. A times b squared is plus ab squared. And again, the order of the variables doesn't matter. However, I recommend keeping it consistent. I usually do alphabetical order so that it's consistent. And then b times a squared is positive a squared b. Then we have b times negative ab is negative ab squared. Then b times b squared is b to the third. We'll just have to combine like terms now. There's no other a cubes, so our a cube will come down. We have a negative a squared b and a positive a squared b, so they're going to cancel out. We have an ab squared and a negative ab squared, so they'll cancel out as well. So my plus b to the third comes down, and as you can see, we have now ended up as the left side of our identity we were trying to prove. So therefore, we have successfully algebraically shown this is true. Okay, so in this example, we're going to factor the expression 9m to the fourth minus 25n to the sixth. Now, We're going to be using identities to do that, but anytime you try to factor, you should check for a common monomial first. In this case, there is nothing that goes into both terms, so we can move on and check to see if this is a pattern. So the patterns that we're going to be checking here, since there are two terms, is the a squared minus b squared pattern, which is the difference of squares, and the a cubed plus minus b cubed pattern, which is the sum and difference of perfect cubes. So with that in mind, based on the fact that the numbers are 25 and 9, I would say it's probably the first one if it is a pattern at all. So let's begin checking to see if it is actually a pattern. If it is a pattern, we'll be able to rewrite it as a perfect square minus a perfect square. So what do we square to get 9? Well, 3 squared is 9. Now this one's a little harder, but what do we square to get m to the 4th? Remember, exponent properties say if you raise a power to a power, you multiply the exponents. So what times are squared would give us 4? The answer to that is just 2. So m squared squared will give us m to the 4th. Similarly, for the second term, what squared gives us 25? Well, 5 does. And then for n to the 6th, again, a power to a power will give us, will mean we're multiplying the exponents. So what times 2 will give us 6? Well, n to the 3rd. So n to the 3rd raised to the second power will give us n to the 6th. So this is indeed a perfect square minus a perfect square. We have rewritten it as such, which means we can apply the identity a squared minus b squared equals a plus b times a minus b. So in our case, the a is our 3m squared, and our b is our 5n cubed. So we'll have 3m squared plus 5n cubed times 3m squared minus 5n cubed. And that would be our answer. In this example, we're trying to factor the expression x to the 3rd minus 216. In order to do this, the first thing we would check for is a common monomial. However, nothing goes into both terms. So moving on, since there is two terms, we would look to see if it's a pattern next. So either the a squared minus b squared pattern, the identity, or the a cubed plus minus b cubed identity. In this case, because this is just a 3 in the first place, and I do believe 216 is a perfect cube, I know it's going to be this second one. So we're going to start by rewriting it as a perfect cube plus or minus a perfect cubed. So for the first term, we cube x to get x to the 3rd. And for the second term, what to the 3rd power is 216? Well, 6 to the 3rd is 216. So we can rewrite both terms as perfect cubes. Therefore, it follows that pattern, which is the a cubed plus minus b cubed. And the other side of the formula, the identity, is a plus minus b times a squared minus plus ab plus b squared. Before I go through using this formula, just a reminder, in these identities here, the plus minus sign is just telling us whether to keep the sign the same or change it to the opposite sign based on whether it's been flipped or left alone. So I'm going to go ahead and apply the formula to this. So our original is x cubed minus 6 cubed. So a is our x, so we're going to have x. The first sign here is the same, so we originally have a minus, so we'll put a minus. And then our b, which is 6. So there's our first factor. Our second factor coming out is x squared, or a squared, which is our x. Then we have the minus plus sign, which means we're going to switch it from the original sign. We originally had a minus, so we're going to put a plus. Then a times b, so our a is x, our b is 6. And then plus b squared, so plus 6 squared. Now, just to make it look a little nicer, I'll simplify my factor, and then we'll be done. So x minus 6, then we have our x squared, not changing there, but x times 6 is 6x, and then 6 squared is 36. So overall, this is my final answer. Okay, in this example, I'm going to factor the expression 8x to the third minus 27y to the ninth. As I factor, the first thing I'm going to check is to see if there's a common monomial in both terms. However, nothing goes into both 8 and 27, and there's no matching variables in both terms. So next we'll check to see if it's a pattern. We'll check the a squared minus b squared, as well as the a cubed plus minus b cubed. Now from here, based on the fact that this one actually does have an exponent of 3, and the fact that I know 8 is a perfect cube, I'm going to be looking at the second pattern, the perfect cubed plus minus a perfect cubed. So I'm going to rewrite both terms as something cubed. So what to the third power gives me 8? Well, 2 to the third gives me 8. And for the variable, x to the third is just x to the third. In the second term, what to the third power gives me 27? Well, 3 does. And then for the variable, what to the third power, or y to what power raised to the third, will give me y to the ninth. Well, remember, power to power means we will multiply the exponents, so I know that that missing exponent would have to be 3. So we can successfully write both terms as perfect cubes, which means it will follow the a cubed plus minus b cubed pattern. As we go through this, the 2x is going to be our a, and the 3y is going to be our b. So going through the formula, we are starting with this side, the perfect cube plus minus perfect cube, and going to the other side. So my first factor is going to be my a, which is 2x, and then keep the sign the same. So 2x minus 3y cubed, which is my b. Then for the second factor, we're going to have our a squared, so it's going to be our 2x in parentheses squared. Then it's going to be the opposite sign. So we had a minus originally, so we're going to have a plus. A times b, so 2x times 3y cubed, and then lastly plus b squared, so plus 3y cubed squared. Because 3y cubed is our b, we need it in parentheses and squaring it. Now we just have to do a little bit of rewriting to make our factor look a little nicer. So remember, exponent properties means we're going to give this exponent to each of the factors in that product. So 2 squared is 4, and then x squared is just x squared. In the second term, we have 2x times 3y cubed, which will give me 6x y cubed. And then in the third term, again, we have the power of a product, so we need to give the exponent to each base. 3 squared is 9, and then y to the third raised to the second, power to the power, we multiply the exponents, giving us y to the 6th. And there we have it, our factored form. Okay, in this example, we're going to look at Pascal's triangle as well as expanding binomials. So if we start off by looking at x plus y to the third, and we try to simplify it, we would write it out 3 times go through the algebraic steps of doing distribution. Since we're multiplying three things together, we would group the first two together and distribute those out. And then take that result and distribute it with the remaining factor. So we'll have 2xy's, and then we'll have a y squared, meaning that our factor is going to be x squared plus 2xy, and then plus y squared. We'll drop down our third factor and do some more distribution. So plus x squared y, then going through 2x squared y, then 2xy squared, plus xy squared, and then lastly, y cubed. Then just combine like terms, we'll have x to the third plus, combining like terms, there's my x squared y's, so we'll have 3x squared y's. Combining these two, we'll have a 3xy squared. And then lastly, my plus y cubed comes down. Now if we take a closer look at some of these lines here, this line right here is x plus y to the third, the sum of x plus y to the third. Now this spot right here was just two of our factors, so it's x plus y squared. And then of course we have just x plus y to the first. If we look at these coefficients, there's a pattern that's going on after simplifying. So if I extract the coefficients for the first power, I'm just going to use n equals 1 to represent the first power. The coefficients with these variables are 1 and 1. In the second power, the coefficients with the first term is 1, coefficient with the second term is 2, and the third term is 1. And when n is 3, or the exponent is 3, we can see that the coefficients are 1, 3, 3, 1. Writing it like this, and if we were to continue it, it would be more clear that there is a pattern going on here. This pattern is known as Pascal's triangle. What's happening here is if you stagger the numbers for each of the rows, the next row is formed by adding the two numbers that are above it. The ends always have a 1 on the end, but the middle numbers will always be formed by adding the two numbers above it. So I can predict n to equal to 4. The coefficients with the power of 4 would be 1, add them to get 4, add them to get 6, add them to get 4, and then 1. And you can continue this pattern indefinitely, just adding the two numbers right above it. It's very similar to Fibonacci sequence, just a little bit more expansive of a pattern. But yeah, it can be used to expand binomials, which we'll do in the next couple of examples. So we're going to use Pascal's triangle to expand x plus y, the sum of x plus y, to the fifth power. So since our exponent is 5, we're going to start with an exponent of 0 and just kind of work our way down. And okay, there we go. And then if it's exponent of 1, we would have 1 and 1, then exponent of 2, 1, add the numbers 2 and 1, and just continue, and our exponent would be 3, adding the numbers, adding the numbers. Then if our exponent is 4, we'll have 1 on the end, add the numbers, add the numbers, add the numbers, 1 on the end. And finally, for an exponent of 5, we would add the numbers, oops, forgot the 1 on the end, add the numbers to find the between one, add the numbers to find the in between one, add the numbers, and then a 1 on the end. So these will be the coefficients with the different terms. Now, as far as the variables go, what happens is we'll start with x to the 5th, and we'll work our way towards y to the 5th. The sum of the exponents will always match the exponent on the outside of the parentheses. So, applying this, we're going to start with x to the 5th. Then we'll have x to the 4th, y to the 1st, or just y. Then we'll have x to the 3rd and y squared. Then we'll have x squared, y to the 3rd. Then we'll have x, y to the 4th. And lastly, we'll have y to the 5th, which would be x to the 0 power as well. Then just going through with the coefficients we found from Pascal's triangle. The first one starts off as 1, 5. Everything's positive here because our original sign there is positive. 10, 10, 5, and 1. And this would be the expanded form of this expression. Now, the binomial theorem takes Pascal's triangle and applies it to be more comprehensive with the different expansions. We still start off by looking at the coefficients for Pascal's triangle. So pulling up the 4th row of Pascal's triangle, we have these as the coefficients. Now, this one's a little bit more complicated because we have 2x and 3, so it's not just variables and not just a number, but we're still going to start off with the same idea. Okay, we're still going to start with the highest power of this first term, working towards the highest power of that term. So we're going to start off with 2x in parentheses to the 4th. Then the next term will have 2x in parentheses to the 3rd times our second term in the binomial, 3 to the 1st power. And it's going to transition into 3 to the 4th by the end, with the exponents always adding up to be the exponent on the outside of the parentheses. So the next term will be the product 2x to the 2nd power times 3 to the 2nd power. The next term will be 2x to the 1st times 3 to the 3rd. And the last term will be 3 to the 4th. Once we have that, we'll go through and just add in the coefficients here. All the signs will be positive, and if this number is negative, that will control what the signs in between are based on the exponents. But all of our numbers here are positive because of the plus sign. So just bringing the coefficients down, 1 plus 4 plus 6 plus 4 and plus 1. Now we just have to go through and actually simplify the terms, and then we'll be done. So 1 won't really affect that first term. 2x in parentheses to the 4th will give the exponent to both. So 2 to the 4th is 16, x to the 4th. Here we have 2 to the 3rd, which is 8. 8 times our 3 is 24, and times the other 4 we have 96 x to the 3rd. In the next term, we'll have 2 squared to have 4. We'll have 3 squared, which is 9. Multiplying those together, giving us 216 with x being squared. The next term will have the 3 to the third, which is 27, times the 2 from the 2x, times the 4, giving us a positive 216x. And then the last term, we have 1 times 3 to the fourth, which would just give us 81. And that would be the overall expanded form of this binomial.